All right, so example 5D. This is where they start getting a little bit more interesting. There's still quite a few things on the worksheet that we haven't gotten to, like when it talks about discontinuities and what types they are. So we'll see if we can get there today. But first we have to look at some of these awesome domain type problems. Okay, so let's take a look at D together. Again, the function doesn't have a particular name. His name is Y. Maybe for Laurel, right? Yanni? Yeah, or Laurel. We have a numerator, right? We're looking for the domain only. Does the numerator come into play here for domain purposes in this case? No. The only time the numerator is going to be relevant for domain is if, for now, if it has a square root or a fourth root in it, right? So what's up, 15x minus 3? We're going to be working in the basement. If you hear any noise, it's us, right? So in the denominator, we do have a square root. So there is the possibility of having negatives underneath there. And we also have a variable in the denominator, so there is a possibility of division by 0, okay? So this would be kind of the double whammy, the 2 for 1. So if we do the analysis very quickly, let's look at the radicand. We get 3 plus 5x squared. We know that has to be greater than or equal to 0. Okay, now for the first time in this class, we have a quadratic inequality. Okay, a quadratic inequality. And unfortunately, you cannot solve quadratic inequalities algebraically. All right, true or false? You can solve a quadratic inequality algebraically. False. Good. Okay. You could solve linear inequalities, that's x to the first algebraically, but remember there's that one caveat. You have to be able to remember to flip the inequality if you multiply or divide by negative. So that's like a fix, but there is no fix to a quadratic inequality, okay? So we have to solve it some other way. And typically we're going to go with the graphical approach, all right? So let's go ahead and figure out what that graph of this function looks like. It is a quadratic, right? It's an x squared, so it's going to be a parent function that is a what? All x squareds graph as parabolas, right? The 5 is just going to, if you remember from Algebra 2, the 5 is going to vertically stretch it by a factor of 5, so it's going to be a little bit narrower, and the plus 3 moves it up 3 units to here. So if you quickly sketch it like that, there is a rough sketch of the graph of 3 plus 5x squared, or 5x squared plus 3. For what values of x is that purple parabola greater than or equal to 0? And by 0, we mean y equals 0, which is also known as the x-axis, right? So for what values of x is the purple parabola above the x-axis? All of them, right? All of them. So 3 plus 5x squared is always greater than or equal to 0. We're never going to have a negative under the radical. Okay, so there's no restrictions there. Got it? All right. So now let's look at the denominator. Remember the denominator, we say that the entire thing shall not equal 0. Well, this is like an equation, so we can square both sides, and we get 3 plus 5x squared then shall not equal 0 squared, which is 0. Refer back to the purple parabola. That's nice and alliterative. Is 3 plus 5x squared ever equal to 0? No, because the purple parabola is 3 at the very least or bigger. It's never equal to 0, right? It's never equal to 0. It's only imaginary numbers that are going to make it 0. So let's see. Do we ever get a negative under the radical? No. Do we ever get a 0 in the denominator? No. It passed both tests, so what is the domain? All real numbers. So we're going to say the domain of y is, now to do all real numbers, it's real easy. You could just refer to the set. And the set has a symbol, that's the double bar R. The double bar R is all real numbers, okay? So that's one way to do it. Or if you want to get fancy, like if you eat Grey Poupon instead of French's mustard, you could say the set of all x such that x is an element of the real numbers. You could do that too. It's kind of fancy. It looks nice. Sometimes it's just fun to make those braces. Or if you're an interval notation person, what could you do? Very good. Negative infinity, comma, positive infinity. Either one of those, okay? Any of those work. All right, so the moral of this story is just because you have a square root with a variable underneath it, and or just because you have variables in the denominator, doesn't mean that you're going to necessarily have restrictions, right? We had both potentially happening here, but yet still no restrictions, okay? So the domain was all real numbers. You actually have to do the math. All right, sweet. That's a good moral. Any comments or questions on this one? Can we solve a quadratic inequality algebraically? No. Okay, good. Letter E. All right, so this one's looking more like maybe what we quizzed over. We have two separate cases. We have a square root in the top, so now that the numerator is relevant, and we have a quadratic in the bottom. So let's do this one together, and then I'll cut you loose on the next one. So let's do the radical first. And we got 5x minus 3 is greater than or equal to 0. Can I solve that one algebraically, that inequality? Yeah, because it is linear. And again, not forsaking that y'all know what linear is. What makes this a linear inequality? The fact that it's not squared, right? It's x to the first. So we can solve those algebraically. So let's do that. That's 5x is greater than or equal to 3. I divide through by positive 5, so I do not flip the inequality. All right, and again, if you wanted to check, we haven't really checked today, but something bigger than 3/5, like 1, you plug it in. 5 minus 3 is positive 2. It works. Okay, and now for the denominator. The denominator, if we factor that after we set it equal to 0, right, that's our setup, or not equal to 0. That looks like it's going to be x plus 3x minus 1. And remember, as you're working down, you need to keep it equal or not equal to 0, okay? 3 minus 1 is 2. Okay, so that works. And so we get straight from here, x cannot equal negative 3, comma 1. And so, like I said on the test, we don't want to doubly exclude values. It may or may not be relevant here, but let's see. We got the domain. This function has a name. His name is f. So d sub f would be the set of all x such that I typically write the inequality first, although in set builder notation it doesn't really matter. And then we only need to exclude any of those two values, negative 3 or 1, if they happen to be bigger than 3/5. 1 is bigger than 3/5. So then we'll just say, comma, x cannot equal 1. All right, so we don't want to, again, doubly exclude negative 3. So on the quiz, both of them fell in the inequality. We had to exclude both of them. But in this case, one of them was already excluded. All right, what would that look like in interval notation? Because I know some of y'all are really liking that. Where would we start? Yeah, it's greater than or equal to 3/5. So 3/5 would be a lower bound, right? So we would start at, I'll just do the whole thing, d sub f, beefy bracket, right? Because it's equal to, so 3/5, comma, cruise all the way to 1, parentheses, step over it, parentheses, cruise to infinity. So again, when you do interval notation, you're not likely to try and doubly exclude a value because it's way down the number line. It's not even really relevant, okay? There you go, either one of those. So, if you notice, the next one is very, very similar, and the next one after that is very, very similar. So let's do these on your own, but I do want to point out that notice the numerator is exactly the same in all three. So what piece is going to be the same for all three of these? The radicand. So for each of these, we're going to get x has to be greater than or equal to 3/5. So you don't have to do that work again. We'll just kind of import that. X has to be greater than or equal to 3/5. So it really comes down to the denominator work. So why don't you go ahead on your own and do that, okay? And again, practice so that you're not doubly excluding any values. I can already see a lot of y'all's notation is coming along nicely. The labeling, the organization, the working straight down, bringing everything along with it. That's good. You've come so far in such a short time already. We're going to need a bigger classroom soon as much as y'all are growing. All right, so in the first one that we just did together, of the two values that gave us 0 in the denominator, we only had to exclude one of them because the other one was already excluded. On this one here, if you set the denominator, again, labeling it denom or denominator or whatever you want to write it, just something to signify you're working downstairs, not equal to 0, it factors this way, and now you get two negative values. Bless you. That was a cough, right, but bless you anyway. Do we have to exclude either one of those? No, -3 and -1, neither one of them are bigger than 3/5. So they are already excluded by the inequality. So the domain of G is just going to be the set of all x such that x is greater than or equal to 3/5. Or, of course, if you like the interval notation, beefy bracket 3/5, comma, infinity. All right? They're already both excluded. And then on the last one here, when you factor it, again, proper notation, not equal to 0, not equal to 0, both lines, you get +3, +1. Are either one of those bigger than 3/5? Yeah, both of them, right? So in this case, the function's name is r, so d sub r. Now it's the set of all x such that x is greater than or equal to 3/5. And then we could say, comma, x cannot equal, and you could say 3, 1. That would be fine. You're excluding both of those. In interval notation, this one gets a little bit kind of elaborate. Beefy bracket 3/5, comma, we got to cruise to 1, step over 1, cruise to 3, step over 3, and then it's smooth sailing forevermore. So those three examples right there, nice review of kind of the entire process, including what we just quizzed over, right? Which was more like that last one where we did have to exclude both of them. Okay, so we don't want to doubly exclude values. We want to think about what we're doing, where our values are, and just be very efficient in our final answer. Okay, cool. Any comments or questions on those? They're getting easier? They're making more sense? Okay. All right, so let's look at kind of a different looking type of function. We've been dealing with rational functions or ratios of two functions. And now we're looking at something that doesn't look like it's a fraction at all. It says find the domain of each of the following. State your answer and set our interval notation. So pretty much the exact same instructions. So take a look at A on your own and just think about the two things we're on the lookout for, what we're trying to avoid, and see if you can come up with the domain. Again, we're not dealing with logs just yet. So it's just division by 0 and even roots of negatives that we're looking out for. Sorry. So if you have something like this that has 3 terms, you can essentially find the domain of each term and then combine your results, because ultimately the domain has to work in all 3 of them. So Do we have any radicals in this function? We do have a radical, right? I see it right there. What is under the radical? Is it 3 or 3x? It's just the 3, right? So you got to be very careful when you're reading, and especially when you're writing. It's very easy to not extend radicals over what you intend to cover. Same thing with like division bars. It's easy to kind of stop short. So you want to be very deliberate in your writing. If you notice, that x is not under the radical, okay, and it's not intended to be. So that's just the square root of 3. So if you look under the radical, we're trying to avoid negatives. Is 3 negative? No. He may have like a negative disposition. He's one of those like, I don't want to be around him kind of guys, but he's not a negative number, okay? So we pass. We pass the radical part. We're also looking out for division by 0. Do we have any denominators? Yeah, technically we do, right? This last term has a denominator, and we're trying to avoid 0 in the denominator. Is 3 equal to 0? No. He's 3, right? At Halloween, if he went dressed up as 0, would that make him 0? He's still a 3 on the inside. We are who we are on the inside. Yeah. Okay. So it passes both. So even though we had a radical, and even though we had a denominator, we passed both of them with flying colors. And if we pass both of those, guess what the domain is? All real numbers, yeah. So you're looking for those two things right now, and unless it's a piecewise function, which we'll get to later, if it clears both of those tests, bless you, then by default, all the other numbers work and the domain is all real numbers. That's the easiest way to say it, okay? Sweet. How about this guy? Let's take a look at him together. His name is G. The independent variable is x. That is 4 to the x power, right? That's how we read that, 4 to the x power. That's an exponential function. Do we have any radicals? No. But do we have radicals in disguise? What are radicals in disguise? What type of exponents? Radicals are not negative. Fractional exponents, okay? So if you notice here, our exponent is a variable. Ooh, could that variable be a fraction? Yeah, it certainly could be. Let's say it was 1/2. If x were equal to 1/2, that would end up that term would be 4 to the 1/2, which would be the square root of 4. So that would put what under the radical? The 4, right? So even though I can possibly have all the fractional exponents I want in the whole wide world, what's going to always be under that radical? A 4, which is always positive. So we passed the radical hurdle. Do we have any denominators? None visible, but we know that denominators can also be what type of exponent? Negatives. Because we have a variable exponent, could x be a negative number? Yes, let's try it out. If x were equal to -1, we'd have 4 to the negative first, but that would be 1 over 4. And now what would we have in the denominator? A 4, not a 0, right? So even though we can have as many negative exponents as we want, we're never going to have a 0 in the denominator, okay? If what was odd? Oh, that would still be okay, right? Because if it were 3 to the x, then that would either be the square root of 3 if I use the top example, or 1 over 3. So we would still have a positive 3 in there. Yeah. Now, for exponentials, you're never going to have a negative base, and you're never going to have 0, because 0 to any power is 0. So because it's a 4, this is good. This passes the test. So the domain of G is all real numbers. All right? So let's look at it real quickly here. Did y'all study exponential functions in Algebra 2? It was supposed to be on the list. Probably. Did y'all study 2 to the x or e to the x? Did y'all have a parent function? Yeah. Well, we're going to study them again this year, and we're going to use base e as our parent function. But maybe 2 to the x was your parent function. We're going to look at 4 to the x right now. Here's what all exponential functions of the form b to the x look like, where b is greater than 1. We call these exponential growth functions. Just kind of a preview of coming attractions. They all have horizontal asymptotes on the x-axis, and they're growth functions, so they look something like that. They all pass through the point 0, 1. So the bigger the base, the steeper the graph. So 4 to the x is a little steeper than 2 to the x. 10 to the x is steeper than 4 to the x. But they all look like this, okay? And so we just showed that the term 4 to the x passes all of our tests. The domain is all real numbers. And if you look at this red graph that I drew, When I first asked about domain, someone said left to right. That's perfect. Because when you have a graph and you're analyzing the domain, that's what you do. You look left to right. So if you look left to right, this red graph is going to live everywhere, right? So for every x value that you do left to right, you'll have a red y value associated with it. So exponential functions are going to have domains of all real numbers all day long, 24/7, 365, okay? And then, of course, the -5 is just a number, so that's good. That moves this graph down 5 units. We'll study transformations again later. So anyway, exponential functions, 4 to the x, all real numbers. Now we know why. Okay, let's look at this one together. The function's name is Hortense, or h for short. The independent variable is t, not x. Do we have a denominator? Yes. Are we at risk of dividing by 0, though? No, because the denominator is a constant. It's 2 square root of 3, which is not 0. Do we have radicals? We do. We have a square root, but what's underneath it? 3, which is not negative, so that one passes. And on the top, we have a cube root. We haven't seen a cube root yet, right? If you go back to our domain, way back up here, when we're talking about what we're looking for, we know that we cannot take a what type of root? Even root of a negative number. But what about odd roots, like cube roots? We can, right? The cube root of -8 is -2. And the reason would be since -2 times -2 times -2, these pair up to give you 4, which is positive. But because it's an odd root, you're always going to have that odd man out, which is going to turn it negative again. So cube roots, 5th roots, 7th roots, odd roots of negative numbers are fine. Okay, but even roots are not fine. So if you see something like this, the cube root of t minus 1, do we need to concern ourselves with t minus 1 being just positive or 0? No. Okay, so if you see a cube root in the numerator, just say, what's up, cube root? Have a good day. All right, so we don't need to worry about it. Now, if that thing were in the denominator, now we need to worry about division by 0, but we wouldn't have to worry about what's under the radical. So if you ever see an odd root index, and it'll show, right, bless you, right there, it'll either be a 3, 5, 7, whatever, you do not have to worry about negatives under that radical, okay? It's only the even roots that we are concerned about. So if it passes then the denominator test, and now it passes the radical test, because it's an odd root, what's the domain? All real numbers. So D sub h is all real numbers. Yeah, very good. Odd root indices. Okay, as easy as it can sometimes be, sometimes we need to roll up our sleeves. I'm wearing short sleeves. And apply a little elbow grease. That's like what old people say. What does elbow grease look like? Are they talking about like skin lotion? Yeah, anyway, I don't know. Okay. Idioms, right? Elbow grease. We have to toil a little bit, which simply means it's going to be a little bit more what? Fun. Very good. Did y'all say hard? No, diamonds are hard. Diamonds are hard. Math problems are fun or challenging. Maybe you can replace hard with challenging. And challenges are meant to be overcome and to have fun in the process of doing that, right? Okay, good. It's all mindset and semantics. Let's try this one. This might be the only one we get to today. Example 7. Guess what the instructions are? Find the domain of each of the following. State your answer in. Okay, sweet. All right, so taking inventory here. Are we concerned with the numerator at all in terms of domain? No, because the numerator never gives us division by 0, unless it's like to a negative exponent. And there's no radical up there. So 9x plus 7 is just hanging out. But in the denominator, we have a variable, so we could possibly divide by 0. And we also have a square root, so we could possibly then have negatives under there. So let's do what we've been doing, right? Just break it down into 2 pieces. Let's do the radical part first, or the radicand, I should say. And the radicand is greater than or equal to 0. Be careful. I still see a couple of people, when we do the radicand, they're taking the radical here. We don't take the radical, just the thing underneath it. Can we solve that one algebraically? Yeah, it's linear, so that's pretty easy. X has to be greater than or equal to 2. And again, if you want to check, plug in a 3. 3 minus 2 is 1. That works. Good. Now, the denominator. This one's a little bit different. We haven't seen one like this because in the past, the denominator has just been the radical. But we have a little helper term down there, don't we? It's radical, and then outside the radical we have plus 1. So remember, for the denominator, we take the entire denominator and say it can't equal 0, the entire thing. Now in this case, it's not going to be wise to square both sides just yet, right? If it was just a radical, we would square both sides. That's what we've been doing. But if I tried to square both sides, I'm going to have to FOIL this out here because it's 2 terms, right? Square, multiply, double square. Gross. So if you learned in Algebra 2 how to solve radical equations, the first step is to isolate the radical. Okay, so to do that, we will simply just bring the 1 across and it becomes -1. Okay, we've isolated the radical. Now we can square both sides. Okay, so the square root of x minus 2 squared is x minus 2, and -1 squared is 1. Yeah. And now we can solve. We add 2 to both sides, and we get that. Now remember, we only need to exclude it if it falls in the inequality. Is 3 bigger than 2? Yes. Okay? But I'm going to put a little asterisk right here. Actually, I'm going to put it right here. I think you learned something back in Algebra 2. If not, here you're going to learn it today. When you square both sides of an equation to solve, you need to check for a solution that might not work. It's called, there, I didn't even finish writing it, and you spurted it out, so I know you've seen it. You got to check for extraneous solutions, okay? Whenever you square both sides, okay, you have to check for extraneous solutions. So here's why. Here's why you have to do that. Let's say you have a linear function like this. A linear function is a line. It can have at most how many x-intercepts? 1, right? It only can cross once. But if you were to square a linear function, it would turn it into a quadratic. And that quadratic might have the same x-intercept you're looking for, but it also might generate a what? Another one that doesn't work. So that's why we have to be careful. When we raise something to a higher power, some of those solutions from that higher power may not work. So let's see. We said that x cannot be 3. Let's try it out. What do you get when you plug a 3 back into the denominator? We're saying it causes a 0 down there. 3 minus 2 is what? 1. The square root of 1 is 1. 1 plus 1 is 0. 2. Not 0. It's 2. My bad, 3. I'm sorry. I colored the wrong guy. I thought you caused a 0 in the denominator. You're causing a 2 in the denominator. So this would be an extraneous solution. All right. So now we have to get in the habit of checking because we don't want to throw out good guys and call them bad guys. So in this case, and I'll show you why here in a second. So therefore, the domain of f is simply the set of all x such that x is greater than or equal to 2. And we do not throw out the 3. Or, in interval notation, it'd be beefy bracket 2, comma to infinity. Now, here's why. Here's why. Notice when we brought that -1 to the other side, on the left side, I have the positive square root of something equals to what kind of number? Negative, right? There's no way that's going to be negative. When I square both sides, I make the negative number a positive number. That's where the error came in. That negative number became a positive number. So there's no way that you're going to take the square root of something that's positive, add 1 to it, and make it smaller to get 0. It's not going to work, okay? So check for extraneous solutions when you square both sides. All right, so that's example 7. We will pick up tomorrow with Q of x for Quentin Pipes of x. Maybe he'll be with us tomorrow. He's still on our roster. So anyway, have a great day. Stay dry. Stay mathy. And have a chocolate milkshake if you can sometime today.